So this video is going to discuss networking and communication systems. So first let's review the TCP, IP, and the OSI model layers. So remember we have these two different OSI or two different network layering kind of systems. And so the TCP IP is broken down into just 4 layers, and the OSI model has 7 layers. But basically, if you look at the top 3 of the OSI, those are grouped together and just called the application layer for the TCP IP. And then the transport doesn't really change, and the network doesn't really change. And then in the OSI model, they kind of break down the physical wiring and transmission and then the communication piece into 2 different sections, which is grouped together in the network interface layer. All right, I also just kind of want to remind you about the different topologies for networking. So we have like point-to-point, the bus, the star, the ring, and the mesh. Now, some different terminology that I want to kind of discuss here. So first of all, we'll talk about data organization. So when sending data between 2 devices, both the devices need to understand how that information is being transmitted. Typically, we send data in groups of bits called a byte, right? Which a byte is 8 bits. And this is like our standard memory size and just our standard grouping. But we also can group them in what's called a word, which is 16 bits. And then we have, but when we send the data as a word, or we can have a double word, which would be 32 bits, or a quad word, which would be 64 bits. But what happens then is we get into this issue if you're sending 2 bytes. The question is, do you send the first half, the biggest half, the most significant bit side first, or do you send the lower side first? And this is true for storing it in memory also. So different types of computers, remember we talked about the different types of processors back in talking about controllers, and we talked about how the different processors process or move the data differently. So when they move that data and you're moving different chunks, the question is, did you grab the chunk on the left first or the chunk on the right first? And there's a term they sometimes referred to as big endian or little endian that you'll see in the documentation, and that refers to how this data is being sent. So when you have 16 bits, as we do here, so the number 320 can be represented as 16 bits, and so that's zeros, 4 zeros, and then 3 zeros and a 1, so that's 8 bits, and then a 0 1 0 0 0 0 0 0. So if we break this into 2 different parts right here, and we send 1 byte and then we send the other, the question is, do we send the byte on the left, which is the high side, the most significant bits, or do we send the section on the left, or I mean on the right? Which side are we going to send first? And so you need to make sure that when whoever you're sending that to, they understand the order that you're sending it, because otherwise those 1s and 0s will get flipped. And so the value of 320 will get, if you flip those, and now your bits, you have the 0 1, it starts with 0 1 because they got flipped on the other end. And so instead of thinking they have the value 320, they have the value 16,385. So the other thing is when, as you even expand it beyond just sending 2 bytes, but you're sending lots of bytes, especially like sentences or fixed long, just very, very long strings of data. The question is, how do we break up that? And so one way that we can do that is we can send it called a fixed length, where we can send a string of data, for instance. So like sometimes, a lot of times, like in a name, we talked about last week about a database and how you have a fixed length character or a variable, a varchar data type. And so this is kind of the same thing. So we can send a group of characters, letters and numbers and things like that, and we can say, hey, we're sending you 25 of these letters or 50 of these letters. Well, we can tell, so that the receiver knows ahead of time exactly how many characters are getting sent. And that way, if if some of your characters are, just like nulls or something, it can still count how many bits and how much information is being passed, because it knows how many are being sent. A different way of doing that is what they call a null terminated string. So what they do, if you go back and you look at the ASCII code when we talked about binary, the very first value in the ASCII code was all zeros. All the bits were zero, and that's called a null. And that's very useful here, because if you're sending a string that can be anything, any group of characters of any sort grouped together in bytes, or if you're sending Unicode, it'd be 16-bit chunks of each string, each letter or symbol would be different. But as you send that, and then they're like, okay, you don't know how long it might be. It might be 10 characters, might be 75 characters, could be 385 characters. So where's the end of that string? And so when we send a byte that's just all nulls, all zeros, then we know that's the end. So that's how we can determine that. We also see, like, when if you've ever worked with like Microsoft Excel files or whatever, they have different types of delimiters to store the data. They have what they call CSV, which is comma separated values. And so if you have like a text file that you want to load into a spreadsheet, into something like Microsoft Excel, you need to make sure you have it formatted in a way that Excel can break it up into the separate columns. And so the two most common ways of doing that is, number one, comma separated values, or number two, pipes. Now the pipe symbol is the vertical bar, and if you look on the keyboard, if you have a standard keyboard, it's usually above the enter key with what we call the backslash. If you have like a laptop keyboard or some other sort of compressed keyboard, they tend to move it around at different places. But the problem with CSV, which is CSV, comma separated values, is extremely common. It's used an awful lot. But it has a huge drawback, and that drawback is that it's separated by commas. But when you're just looking at ordinary text, we use commas all over the place. If we're putting in a number like, say, 1,273, a lot of times we'll type it in with a comma, right, to separate the 1,000 from the rest of the number. Things like that. Or just if we're sending ordinary text or whatever, we use commas all the time. And so what happens with a CVS file is you get this, you have to, commas isn't enough to tell where it ends, and so then you got to put quotes around it. So it makes it much more complicated. Now on the other hand, this pipe symbol, you may have never even ever used this pipe symbol. It's very uncommon to be used for It's certainly not used in ordinary text or typing in numeric values or things like that. So that's why the pipe symbol makes an excellent delimiter to break up sections, because it's virtually not used for anything else. We also have advanced formatting like XML or JSON. Okay. All right. Now, when you send communication, we could have state communication or what's called stateless communication. So remember that the concept of today's lecture is we're going to be sending out data, and the question now becomes, if I'm going to send information out to some other device, is that device even turned on? And if it is turned on, is it communicating? So we don't really know. The sender doesn't necessarily know whether that other machine is up and ready to receive information, or if it knows who I am or who the local machine is. So another term is communication overhead. Okay, so when you're going to send information, you want to send just a value. Okay, well, that's all fine and dandy, but the question is, we've already talked about encapsulation. When did you encapsulate? You have to put in the address, not only the address of who you're sending it to, but you got to put in your return address and all this other stuff. So this is overhead. So I have an analogy of this. Consider we're going to take a trip to the White House, right? So I sent my letter, if you remember from the other lecture, right? I sent my letter to the president, and he liked my letter so well, he invites me to the White House for dinner. And so I have two choices on how to get to the White House. On the one hand, I could simply just get in my car and drive. So I used Google Maps or whatever. I did a search here and found out that, the estimated time to drive to the White House is 5 hours and 58 minutes. Now, on the other hand, I could fly, right? I could go to the airport and fly. So flying, it's only going to take an hour and 20 minutes to get to Washington, D.C. However, does that mean it's just going to take an hour and 20 minutes to be in the White House sitting down with the president for dinner? Not quite, right? There's all this extra overhead. Number one, you're going to have to purchase your tickets, so you might, a lot of times if you've ever tried to travel, you spend half an hour or more just trying to find the best flights and the best price. Then you're going to have to drive to the airport and then park and then walk. Okay, so, and then, they always tell you, if you're flying, commercially, you're going to have to go through security. So they always tell you, you better get there 2 hours early just in case it takes you a while to get through the security. Okay, and then and then if you're taking luggage with you, you're going to have to wait for them to get the luggage off the plane, and then to the baggage claim so that you can claim your luggage. And so if you add all that up, okay, and then of course, I forgot, we're still at the airport, so then we're going to have to get a cab or an Uber or something so that we can actually get to the White House. And so if we add that all up, and again, this is just an estimate, but I came up with about, something like 5 hours and 22 minutes. So then the question is, that it really, that 1 hour and 20 minute of flight time, it's like, well, that's fine, but in reality, it took me over 5 hours to do that. So then it's like, well, it's almost the same as just getting in the car and driving. But that's what we're kind of talking about for communication overhead. So the same thing is when we're, we just maybe want to send 1 bit to the PLC, right? Like so we just want to tell the PLC, uh, you know, turn on or off, kind of like what we did in the Ethernet lab, right? We had those 4 programs running, and we sent it a bit for program 1, or turned on a different bit for program 2 or whatever, and we were able to send it just a 1 or a 0 to tell it to run this program and don't run that program. Uh, but to get there, right, the computer, it had to throw in the IP address and the port number and all this extra information that had to be encapsulated in there. And so the more complicated that encapsulation is, the more overhead that you have, and then it's going to take longer to send the data, and you're going to have to do more processing on both ends. All right. So another term, I don't know if we mentioned this before or not, but it's called API. API stands for Application Programming Interface. So typically when you're trying to like do any sort of programming or whatever, you're going to make use of this API, which is this interface that's provided to you by whoever created your programming compiler tools. And they give you these extra libraries and things that you can do. So API is actually more general than that. API is just a standard saying, look, you have to do A, then B, then C, then D. So it lays out the process that needs to be done for communications to happen. Okay. And so to kind of give an analogy of that, consider that, all the different cars on the road today. We have lots of different cars, and they have different engines. We even have electric cars with electric motors and stuff. So there's lots of differences. If you just look at cars driving by on the road, they have lots of differences. But on the other hand, they have some standard things, right? They have a steering wheel. They have some kind of ignition or system start. They have brake pedals and throttle pedals and turn signals. So these are the kind of requirements that are specified, for the API, where you have to have these things, and they have to sort of be in this order. And then, of course, there's the concept of real time. We've discussed this before here, but we have what we call hard real time, which means that the data is being delivered within a guaranteed time frame, or soft real time, where the data is being received regularly, but if we don't get an update every now and then, it's not the end of the world. Okay, so if we want to share our information across the internet to another device, there's lots of different APIs, right, interfaces that can be used. Here, I'm just mentioning 2. I'm not saying this is all of them. This is just 2 of them here. But we have one called REST. And again, REST is an acronym. I forgot what it stood for here. But REST is an acronym that is very well used. Basically, anytime you open up a web browser and do any searching or go to Amazon to buy something, anything like that, you are using these protocols within this REST API. And so it's very well known, very well used, but the catch is it has a lot of overhead. Now, some of that is good because, pretty much everything that we're doing through a web browser is encrypted, for one thing, although that's not technically REST, that's another layer there. But the, we're able to go to Amazon and buy all these things and put them in our cart and then purchase them, and then when we purchase them we have to put our credit card information in and our address where this stuff's going to be shipped and all that. And all that is all defined within this REST protocol. So it's being able to buy things online and things like that is just wonderful, but there's a lot of overhead that we don't really think about on top of that. What we're going to focus on here is something called MQTT. MQTT is, again, that's an acronym here. We'll look at the full name in a minute here, but it's a lightweight protocol that has virtually no overhead other than what you personally decide to put in it. Okay, so MQTT, originally it was an acronym that stood for Message Queuing Telemetry Transport. Now, most people don't even think about that or remember that. A lot of these acronyms, it's, that just becomes kind of a name. MQTT, that's the name. So this was originally developed by IBM, but now it's been taken over by this Oasis group that is kind of a conglomerate group that specifies any changes that you may want to make to that. And so there's a couple of different versions. Well, there's a lot of different versions, but there's just two that I want to discuss here. There's version 3.11, which was actually kind of standardized by this Oasis right after they took it over in 2014. And this one is currently being used by most devices. And then from there, they've been upgrading over the years. And there's like a version 5 that was actually released 6 years ago. So there's probably newer versions now. But version 5 added a lot of extra features that weren't available in this original 3.11 version. But like I say, a lot of the devices that are still being used are kind of older devices that haven't been upgraded, and so they're still using this 3.11 standard. So they don't have some of the additional features, but they're still very useful. All right, so when we talk about those layers again, remember that the TCP protocol, this was at that protocol port layer. We have this, we're going to transmit this data. And so the MQTT by default uses an unencrypted port of 1883. Now, if you remember, our node red is actually using 1880. All right, so don't get those confused. So 1883 is the port for MQTT protocol. Now, this is the default port. You can always configure to use a different port if you want. That gives you a little bit of added security because hackers don't know what port you're using. So if a hacker or something maybe was trying to get into your system through 1883, they're aware that this port uses this protocol. So that would be sort of an advantage of moving the port number, but then you got to make sure that everybody knows you've moved it. But anyhow, so this unencrypted port is 1883. If you want to do encryption, that by default uses port 8883. And again, some, they can be moved to other ports, but they're typically in that range for encrypted. So there's also a kind of a specialized version of this called MQTT-SN, which is focused primarily for sensor networks. Okay, and it's targeted for very low power, battery powered devices on non-TCP/IP networks. So we're not, we're talking about we're not going to transmit the data on Ethernet, right? So this is low power low. We're just sending sensor data. We're sending things like what is the current temperature, what is the current humidity, right? Just little chunks of information. All right. Another cool thing about MQTT is you can do what they call one-to-many communications, or many-to-many. So when you send the data through MQTT, you're sending the data to what they call a broker. We'll see that in a minute here. You send it to a broker, and when you send this data out, it gets to the broker, and then if multiple people want to read that data, all they got to do is go to the broker and subscribe. Okay. So the MQTT uses what's referred to as a publish subscription technique. Okay. So what you do is you lay out a topic. The topic is a name that you use, and you can choose the name of your topics yourself. So, they can be totally unique, but if you use like generic names, other people might be using them also. But the idea is you kind of lay it out in a hierarchical structure, kind of like files on a hard drive. And then you have clients subscribe to a particular topic. These clients then publish information. If they want to send information out, they send it to that topic, to the broker, and then anybody who wants to receive that information, they have to subscribe. And then as the client sends the data, everybody who's currently subscribed will receive a copy of that information. All right, so the advantage of using a broker now, it allows the passage of messages both ways so the client can send a message out, and whoever wanted to receive that message can receive that message. And the beauty of this is that you're not compromising your firewall, which is your security, into your personal networks, because you're not opening a port and the messages aren't coming directly to you. You're going out to the broker and saying, hey, is there any new messages? Give me a copy. All right. Now, anytime you're doing communications, a lot of times they use, I think I may even mentioned this under the microcontrollers thing, there's something called a heartbeat or a keep alive. And the idea here is to, when you open up communications, you want to know, you need to keep that communication open. And so that's done through what they call like a keep alive, or sometimes a heartbeat thing, where you just send out a little pulse every so often just to keep the communication open, so that when a client actually publishes the message to the topic, you're subscribed to it. So by being subscribed to it, you're sending this pulse every so often saying, hey, I'm still here. Is there anything new? And if there's nothing new, it takes very little bandwidth. It's just basically saying anything new every, once a second or whatever. I'm not sure exactly what the timeline on it is, but, once a second or once every 30 seconds, you say, hey, I'm still here. Anything new? And if there's something new, then the broker will pass it on. So this is kind of a graphic of what happens here. So over here we have different things that maybe they're sensors or whatever, that they have information. They publish that information out to the broker. And then over here we have different clients that have subscribed to that particular topic. So both of these two sensors, for instance, could be sending to the exact same topic, or they might have their own topic. But you publish to these topics, and then as you publish to the topics, anybody subscribe to that topic, again, as when they send out that heartbeat, and then if there's anything new, the broker says, okay, yep, I got something new, and they then will pass that on over to the subscribed. So MQTT uses something called quality of service. Now, a lot of other protocols use something of this nature also. But for MQTT, they have what they call quality of service. And this quality of service kind of has to do with what happens when you receive that message. So the problem with MQTT here, this is kind of the catch, is the fact that you have this subscriber is subscribed, and then you have the sensor that publishes the data, and then the data gets sent on. But what happens if the subscriber loses communication? Okay, so this sensor is trying to publish this data, and what it does is it publishes out to the broker, and the broker has that data, and then everybody currently subscribed gets the information. But you kind of get into a thing here now that what if the person subscribed wasn't connected for some reason? They lost network connectivity, or they shut down, or whatever. And that's where the quality of service comes into play. So there's like 3 levels of this. So a level 0 indicates that the message should be delivered no more than once, but it's okay if it doesn't get delivered at all. So if the subscriber was disconnected, that information gets lost. Okay. If the subscriber is connected, we're going to send them that message, and if maybe something happens where they sort of lost connection, they may get the message delivered more. They won't get the message repeated. Okay. But like I say, the data could be lost, and so therefore, the advantage of this quality of service is that the data being sent, you're only sending it once. There's no repeat sending, and so therefore, if the subscriber didn't get the data, they didn't get it, but you're not wasting battery life on your sensor devices, and you're not wasting communication bandwidth on your network. So, typically this is very common for something like a temperature sensor, because, it's sending out data once a minute, or once every 5 minutes, or every 15 minutes. And if you miss the data, it's no big deal. You can wait, and, 15, 20 minutes later, it'll send out the data again, and you can catch it online at that time. All right, so there's the second layer is a quality of service 1, which indicates that the message is guaranteed to be delivered at least once. All right, but now then the case says, okay, well, I think I sent this to you, but I'm going to send it again just because I want to guarantee that you received it. And so then what happens is that you could receive the message multiple times. So now it's up to the subscriber who's getting this message multiple times to determine, is this the same message I got 30 seconds ago, or a minute ago, or 15 minutes ago, or is it a different message? And so, and again, this kind of gets into that overhead we talked about before. So one of the things that you might do now when you send the data is you may send like either a timestamp with it, or some other indicator data that you package in with the temperature, but you send a timestamp or some code. So you say, okay, you've received this, and so the person receiving it can then compare that to the one that they received before and say, oh, these are identical. It's not just the identical temperature, but these are the identical message because they have the same timestamp or they have the same code in them. And so I know it's the exact same message that was repeated as opposed to the same temperature but at a different time, something like that. And then there's quality of service number 2, which indicates that we're going to guarantee that you get the message, but we will not repeat the message. All right, so as I already kind of mentioned, right, the advantages of MQTT, number 1, it's very lightweight, so it's good for low-powered devices like sensors and things that maybe are running on batteries. Okay, it's easy to program and configure. Okay, so it's very, very simple to set this up and get communications going. The publishing client does not have to be active when another client is subscribed, okay? Because you're not talking to the subscriber. The client's not talking to the subscriber. Neither one of them are trying to talk to each other. So you've got this middle man kind of set up which they call the broker. And so the client is sending message to the broker, and the subscriber is subscribing to the broker. They're not subscribing to each other. So if one or the other is down, it's no big deal. If the broker's down, then you have no communication. So that's a big deal. But if the broker is up and running, the client and the subscriber can disconnect, or the publisher and the subscriber, they can disconnect, they can be offline, and then they can reconnect, and there's no big deal. All right, and so the big advantage, or one big advantage of this anyhow, is that it allows safe communication through firewalls. All right, and so there's no hole. You're not poking a hole in your firewall to do this. Okay, now the only catch there is if you're actually doing this through the internet, you need a broker out in the cloud, outside of the firewall. All right, so you can set up a broker just internally to pass data back and forth using this protocol. But if you want to do it across the internet, you must have a broker out in the cloud. So you're going to have pay for some sort of cloud access to run this broker on. Okay, so this works with or without encryption. Okay, so if you have a temperature sensor and you're sending temperatures, you could send that data encrypted, but to do encryption, number 1, you're going to have a more powerful processor that can actually do the encryption, and it's going to take more battery juice. So if this is like some kind of remote sensor, and all you're sending is temperature anyhow, then you probably really don't want to mess around with encryption. It adds a layer of complication, and it requires more battery, and it requires more processing power. All right, so it's like, okay, I don't care if anybody intercepts temperature data. This is the temperature out here at this location. So so you have to decide. Now some data you might be trying to send does need encrypted, but it's up to you to decide what needs it or what doesn't. The other thing is that MQTT is designed for very, very small information. So you can send as little as just like 2 bytes of information. All right, so it's actually designed to handle a word, one word, which, like I say, can just be the temperature, or temperature and humidity, maybe 2 words or whatever. but it's limited to like 256 megabytes, which is actually kind of large, but it's not designed to send like a video. You can't send video 256 megabytes. You can certainly send like some image data or whatever, but not a ton of information. And it's certainly not like geared for streaming or anything like that. All right, some of the disadvantages. As I just mentioned, it can't do video streaming. Broker issues. So you have this broker out there, which if the broker goes down, you have no communication. Now you could publish the data to multiple different brokers. So if you just have one broker and it goes down, you lose communication. But you could set up multiple brokers in case one goes down, you have another one. So your client now would have to actually publish to both of those. Okay? Or you would maybe kind of have to set up a repeater alongside the broker. So the broker doesn't necessarily repeat the data, pass the data back and forth, but it wouldn't be hard to, if you had two different computers out there, to set up one or both of them to say, okay, we're going to subscribe to all these topics and then share that data. The other side is that in the nature of MQTT, you send the client publishes that message out. It's kind of a broadcast. There's no automatic receipt that the subscribed client received anything. All right, so where like that REST protocol that we talked about earlier, that has again, it has a lot of extra overhead built into it, but that overhead includes things like error checking and also guaranteed receipt. So when you connect to the remote system, you're going to get a response back that the remote system, you've actually connected with them and they've received the information. So that's all built in, where MQTT doesn't have that built in. It doesn't mean you can't do it. It means that you have to set up, okay, well, if I'm going to send this data, publish this data out, and this subscriber is supposed to receive it, then you have to have that subscriber then publish a reply saying, hey, look, I received this, so that the message went there. So it's on you when you set up this communications. It's not built into the protocol. The other thing is that it's not designed for real time. So remember, we talked earlier about this concept of real time. MQTT is, we're sending the data out to this broker. So number one, we got this middleman sitting out there. So there's a third party that's going to delay the message, number one. And so number two, there's no guarantee that the subscriber actually received the message. And so there's latency in this system here. So it's not designed for hard real-time communications. It's designed for sending the information, and it's reliable. I'm not saying it's not reliable, but it's not guaranteed to get there within a critical time to stop something, shut off a system before damage or overflow or something occurs. All right, so some of the alternatives are what we call hypertext transfer protocol, which actually that REST that I mentioned is kind of built on. There's also another protocol called constrained application protocol. HTTP is large overhead, meaning it does usually it's done with encryption on top of this, and it's got the guaranteed delivery and things like that, but it has a lot of extra overhead on it, so it doesn't really apply for like little sensor devices. This constrained application protocol, on the other hand, is a lightweight protocol designed for smaller devices with low power, especially ones that aren't powerful enough to use HTTP. They can actually send message as small as like 4 bytes, but it's not quite as reliable as MQTT. But I've never actually worked with it myself, but it's another option that's out there that you may want to consider when you're looking at different things. So here's a little comparison. Okay. All right. So with the MQTT, as we already talked about, it's a publish subscribe model. This CoAP is request response. So you request a message, or so if you're requesting the temperature from your sensor, and then the sensor has to respond. The problem with this is the sensor, again, if it's a remote battery operated system, it may be going down into a low power mode and not be listening. So if you go out and request a temperature and it's in low power state, it's not going to respond. Where the MQTT, the temperature sensor goes in a low power state, and then it wakes up and then publishes the data and then goes back to sleep, and we're not looking for a direct reply from that. Okay. CoAP is designed for basically one-to-one or peer-to-peer or machine-to-machine sort of communications, where the MQTT is like a many-to-many or one-to-many sort of thing, where it's like, okay, I'm going to send this data out, and a lot of different machines or a lot of different people could receive it. Okay. CoAP is also, it's asynchronous or it can be synchronous. So it can be either, where MQTT is designed to be only asynchronous. Okay, so because this is synchronous, this could be used for at least more reliable real-time kind of communications. Okay. All right, another alternative is something called XAMPP, which is Extensible Markup Language. Okay, so it's built on top of the XML formatting that we talked about. So it has some extra layers on the way the data is sent out. Okay, and encryption is built within the protocol. So if you're, if you really need encryption, this has the encryption built within it. Where if you wanted to do encryption with MQTT, you could do that, but again, you would have to do the encryption, then use MQTT to send the data, and then the receiver would have to receive the encrypted data and then run it through the decryption on the other side. So you would have to handle that. Well, and again, you can do encrypted MQTT, where it will handle it if you set that up. But there's extra overhead to setting up encryption. So the same with this. This has extra data, but this is more of a peer-to-peer, this is kind of like between the two there. It's got peer-to-peer communication like the CoAP has, or you can do a publish subscribe sort of model, more like MQTT. Okay, and again, there's just lots of different ones here. This is just another one here. It's called AMQP. This one is an efficient protocol using a broker or peer-to-peer, and it supports distributed configurations on there. So it's very similar to the MQTT format. Another one is called DDS, Data Distribution Service. This is intended for industrial. Okay, so this is dedicated specifically for industrial IIoT with very high data rates. So this is designed for more data than the MQTT or the CoAP. Okay, it's also designed specifically for real time. So it's not using a broker, it's not using the middleman, it's more of a peer-to-peer communication, low latency, which goes along with the real time, extremely reliable, highly scalable. Okay. All right, so this is just kind of a layout for the DDS here. So down here at the low end, you have your devices or sensors that are have the data, and they're sending that data back and forth, and then that data can be sent to the next level up for subsystems and advanced control and processing, and then it can be passed on up to a higher level for supervision, managerial sort of applications, and then it could be sent up more into like the cloud area for data analytics and machine learning and high processing. All right, and then here's that REST protocol that I mentioned, and I've got it spelled out here. So again, it's an acronym. It stands for Representational State Transfer. Okay, this is a point-to-point. So it's a client server. So you have the client is connecting to a server. Okay. And so it's a point-to-point in there. And so if you're going to send this out to the cloud, you have to have the server would actually have to be outside of the network. Now it's stateless, which means that we don't really know what the state of the person we're sending it to, but we're going to connect to the server and send the data. And it usually runs using that HTTP or the CoAP protocols that we mentioned earlier. And again, the advantage of this, it's a standard API that people have been using because it's what the internet uses. So if you have somebody who develops websites, they're very familiar with this. It's a good way to send data up to the cloud, but it's it's definitely not real time. All right, so when I said this is stateless, basically what that means is each time the client wants to make the connection, it has to reestablish the connection. So this is kind of different from the MQTT. Remember, the subscriber has already been subscribed to that topic, and then they're sending this heartbeat signal to keep the communication established. Here, we're sending the data. So when we send the data, we're going to connect, and so we know that the server is there. But then after we send the information, we shut down the communication. We don't keep a heartbeat or whatever there. We just close that communication. And so when we want to send new data, we have to reestablish that communication over and over again. And that adds more overhead to each connection. And again, the server cannot send messages to the client. The client has to go to the server and say, do you have any messages for me? But again, the difference here is we don't have an established connection. We close the connection, so we have to reopen a new connection every time we want to go ask if there's any information. Where with MQTT, when you're subscribed, you're just sending this little heartbeat. Hey, got anything? And as soon as something is available, it will get forwarded on, or at least within the next heartbeat. Okay. So here's just like a little comparison thing here. So I'll just let you read through that. Okay. All right. So there's a link here that I put that I recommend that you go read if you're going to do MQTT, and it just gives you some list of best practices. Okay, so and it actually talks about some wild cards and things that are available, and some things that you should or should not do if you're going to be using MQTT. All right, so for our lab, we're going to use this site called Mosquito, and this is a play on the acronym MQTT. But they set up a website called mosquito.org, which allows you to connect to a broker out on the internet. So you're going outside the firewall, and you can create a topic on this website and then connect to that topic and publish to that topic, and you subscribe to that topic and pass the information. And there's no cost to this. However, this is a free server, and you never know for sure whether it's going to be there or not, right? So you wouldn't want to use this for your company because they may shut down, and then you wouldn't have any communications. So in the node red, there's two nodes that are for MQTT. So the first one is an input. So the input here is a subscriber. So you're going to subscribe to a topic. Okay, so you're going to subscribe to a topic. So in this case, I'm subscribing to the test.mosquito.org, and then the topic is off screen here. You can't see it here with this block here, but I'm going to subscribe to a topic. And then over here on our output node, this is the publisher. And so you can see here I'm publishing to this node. I'm publishing to test.mosquito.org, and I have my topic here. And so, I over here, the subscriber would have to be subscribed to that topic. It's just not showing on the screen. All right, so that's it for